been silent because I forgot to flip a switch. Now it's good. But those were just terms, so we are not losing a whole lot. All right, so turn on the tablet. And now you know my password to get into my tablet. And where's my little pencil? Right there. There we go. All right, so this is from my other class. Let's go back to this class, 440. And 189. Nope, that's the exam. Okay, back. 418, there we go. All right, so we can look at a trial like a coin flip, okay? So coin flip, one flipping of a coin is one trial. So if that is a trial, what are the outcomes? Heads or tail, exactly. So the outcomes for each trial is either a head or a tail. That's it. Okay, so that's the relationship between a trial and its outcome. So are there any questions about what constitutes a trial? It's basically attempting to do something or an action doing something, and then the outcome is basically what can possibly be the results of doing that something. Okay? So what about experiments? So an experiment is a series of trials. So now I can define my experiment. Okay, so I think I can now design my experiment to be, let's say, just 4 flips. Okay, 4 coin flips. So in that case, if that is one experiment, what do you think is the set of possible outcomes of the experiment? There are 4 flips for each experiment. Yep. Yep, exactly. So there are 16 possible outcomes, and I'm not gonna. Yeah, go ahead.
Oh, so it's 2 to the 4, basically?
It's 2 to the 4, exactly. Because in this case, as we'll see later, this kind of experiment is with replacement. In other words, if the head shows up, in the first flip, can the second flip also end up with a head? Yes. Okay. So that's what we call with replacement. So the outcome set is going to be head, 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 tail, head, head, tail, head, and so on, and then tail, 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 tail. And there should be 16 of these items. So is that okay? I mean, does everybody understand the term, outcome, as opposed to the terms of trial versus experiment? Okay, that's good. All right. So if those terms are okay, then we continue with the notes here. And now we get into general counting. So when we are dealing with general counting, we'll deal with the easier one first. So the easier one is with replacement. And what I'm showing here is if you know the individual outcomes of an experiment, so T0 is the set of is the outcome of the first trial. T1 is the outcome of trial 1, trial 2, and so on. So when you want to look at the outcome of the entire experiment, which involves m trials, it's just the Cartesian product of all the individual ones. That seems to make sense, right? Because if the first trial can have, A, B, C, D as possible outcomes, and then the second trial, let's say we have X, Y, Z as possible outcomes, then the Cartesian product of those two becomes, the set of all possible outcomes of the entire experiment. Is that okay? So that seems to be pretty easy. And the Cartesian product is used because for every element in T0 as the first actual outcome from the first trial, every F as an experiment of the second trial, T1, can be the outcome of the second trial, and so on. So that's why we are using the term of using Cartesian product in this case, because each element of one set can be paired up with every element of the next one. Okay? So how does this help with counting? In other words, this is not showing us anything about counting, because in terms of counting, we only want to know the cardinality of this entire thing. So how do we figure out the cardinality of the entire Cartesian product? Well, that's pretty easy, because all we have to do is to multiply the cardinality of each individual one, and so the product of all of these trials, or the products of all of these, the product of the cardinality of all the outcomes of the trials becomes the total number of possible outcomes. Is that okay? All right. So are we still okay up to this point here? Does everybody understand the big pi notation? Yep.
So for heads and tails, the cardinality of any trial would be 2.
Yep.
And then we just multiply that by how many times we flip the coin.
Yep. Exactly. So that is a special case where the cardinality of all the TIs are identical too.
When wouldn't they be?
It depends on. Sometimes it may not be the same. Okay. So that's why in the next paragraph it says, in some cases the set of outcomes are the same for all the trials. So we have T0 equals to T1 equals all the way to T m minus 1. The sets are the same anyway. Okay. So they have the same cardinality. So that's why if I assume n is the cardinality of T, which is the same for every single trial, then in this case the cardinality of the entire experiment, or the cardinality of the outcome of the entire experiment, is just n to the power of m. That seems to make sense. Okay? Now we have seen something like this already when we talked about the birthday problem. Remember that? And I want to know, how many ways can we assign birth dates with a class of, let's say, 40. And I don't really care about whether we have 2 people or 3 people of the same birthdays or not. Okay, so I just want to know how many ways can I assign birth dates to people in the class. Duplicates are possible. Then there are 365 to the power of 40. Because each person can choose one day out of the 365, but the next person can also choose any one day out of the 365. So in that case, this formula works out, okay? Because n is representing the cardinality of each trial, or the outcome of each trial, and then we have 40 trials because we have 40 students in the class. So is that okay? Is this relating back to the birthday problem that we talked about on Monday? Okay. Yep. Okay, the pi part is just multiplication. In other words, it's a shorthand for multiplying things together. So if I switch back to the tablet, I can just explain what it means. So we know about sigma, and this is about the same thing as sigma. So let's say this goes from 0 to n, and then whatever here is, I just call this a function of I. Okay. So this is really the same thing as f of 0 times f of 1 times f of 2 times blah, 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 all the way up to f of n. As opposed to sigma is an addition, this is a multiplication. Yep. Yep.
What do you call this? Sigma, what's this called?
Pi.
Pi?
If you want, if you prefer, we can call it big pi. Because we know pi as the small pi, the lowercase pi is what we use as the constant. So this is the big pi. This is the capital pi. Yep. Yep.
When you were talking about the Cartesian product, it's like in the one we were just talking about with 16 outcomes, it's like ht Cartesian product, ht Cartesian product, ht Cartesian
Right. Exactly.
product.
Yep, yep. So that's exactly the point. Okay, so if you talk about 4 trials and each trial is tossing a coin, then the first trial has this as the outcome. The second trial has the same set as the outcome. So after 4 trials as an experiment, then you end up with the Cartesian product of 4 of these things. Okay, and the Cartesian product of 4 of these things would look like, tuples in 4 tuples: head, 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 tail, head, head, tail, head, and so on. So I just didn't use the parentheses and the proper syntax for tuples. So I just kind of string up all the letters together, because otherwise it just takes a lot longer to write out the entire thing. So are we still doing okay so far with all this stuff? Okay. So if this is okay, then we talk about the special case, or not so much special case, but the other case where you are running experiments and it is called without replacement. In other words, whatever you have chosen from one trial is no longer available to all the subsequent trials. So what kind of problem has a nature like that? Lotto. Yep, go ahead. Sorry? Yep, pulling cards out of a deck is like that, without replacement. So it's different from pulling a card out of a deck and then putting it back in randomly. Okay? So the text here describes it as a common restriction to trials in one experiment is whatever is chosen in earlier trials cannot be available as a choice for later trials. So it's just like in Lotto. After you pick up a particular ball from the basket, that is no longer available. It is now set aside, so it is called without replacement. So in this case, we'll make an assumption and say that we start with a particular set T, where the cardinality of T is just abbreviated as N, as the set of outcomes of the very first trial of an experiment. And we say that we have M trials in this case. So once again, we have N available choices for the first trial, and then we have M trials. So are we good so far? So I'm using the same letters for the same meaning as the previous case. But the problem is, if a particular element is chosen in the first trial, it is no longer available for the second trial. So that means in the second trial, we are looking at T minus and then the set of E0 in this case to basically say, whoops, that particular element is no longer available. You can choose from the rest of T. Is that okay? So the number of choices available for the second trial is just going to be N minus 1, because we had N to begin with. 1 is now taken, so we got N minus 1 available choices for the second one. So using EI, E subscript I, to represent the actual outcome of trial I, then we can see that for trial I, the outcome set is the following. So let's find out what this means, okay? Because this is once again using some notation that may not be obvious, because we usually do not use a symbol like this. So we have set T, which is the set of all possible outcomes for the very first trial. And then we have the subtraction here. This is a set subtraction. In other words, we are looking at elements that are in T but not in whatever is in the parentheses. Okay? What is inside the parentheses? Oh, it's a big U notation. So we got the big sigma notation for summation. We got the big pi notation for multiplication. What do you think the big U notation is for? Union. So it's for union, okay? So this is basically a gigantic union of the following items. What items are we talking about? Well, we are using an index called J. J goes from 0 to I minus 1. Okay? So what's inside the set that we are combining? Each set is really just a singleton set, which means it only has one single element, and that one single element is E subscript J. What is E subscript J? According to this notation, E subscript I is the actual outcome of trial I, so E subscript J is the actual outcome of trial J. Is that okay? Does that make sense? Okay, so I'm really just using mathematical symbols to represent what are the choices available for trial I? In very simple English terms, it's everything that is left over from the previous trials. That's all this mathematical notation is trying to say. Are we doing okay so far with this? Yes, sort of. Okay. So how many choices do we have left in terms of cardinality? So we're just applying the bars around this entire expression and say, okay, if I don't really need to know the exact elements, I just want to count how many elements, what do we need? What do we know? Well, T starts with n elements, right? And then the union of all of these things is guaranteed to be just I. How do we know that none of these two sets will have the same element? Because not exactly. It has to do with how these elements are chosen by themselves. So EJ is the actual outcome of trial J. But remember, all of these trials are without replacement. In other words, once you have chosen a particular element, it is no longer available for the later trials. So that's why I can guarantee that none of these sets here is going to have any overlap. So the union, or the cardinality of the union, is really just the addition of the cardinality of each set. So that's why the cardinality of this entire thing is n minus I. So are we still doing okay, or should we stop a little bit? Is that okay? Now I can give you an example. Okay. So let's go ahead and work with an example. So this way we can relate the symbols to something that's actual. Okay. So we'll go use lottery as an example. Okay. So in lottery, in Powerball, how many numbers can we choose from? It's from 1 to 69. Okay. I think it's 1 to 69. Okay. So we have one. I'm not going to write all the numbers. To 69. Okay. So that's what is available to the first trial. Is that okay? So we'll just go ahead and say E0, which is the outcome of trial 0. Okay. Now this is specific to a particular experiment. So the next experiment can pick a different element. But in the first one, I'll just say we're picking 16. Okay. So now what would be T1? In other words, what is available for trial 1? Well, we got everything in T except for 16. Okay? So that would be T minus the set only consisting of 16. It is not T minus 16. It has to be 16 in curly braces, because the subtraction operation operates on two sets, not a set and an element. Yep.
So T0 would be the top one?
Yep, T0 would just be T itself. So T0, which is representing the possible outcomes of the first trial, is really just T, because we have not used anything at this point. Is that okay? So now we have to say, well, let's say that we pick 57, okay, from trial 2, or the second trial 1. Okay, so now what is available in T2, in the third trial? T minus the set of 16 minus the set of 57. That's one way to write it, but there's one more way to write it. It's T minus the union, the union of the set only with 16 as an element and the set with only 57 as an element. Is that making any sense? So in the third trial, we have to say not everything is available, because in trial 0 we use 16 already, so it's not available anymore. In the second trial, or trial 1, we use 57, so that is also not available. Yep.
So it would be wrong to say that T2 equals T minus T1.
It would be wrong to say that T2 equals to
T minus T1.
That would be incorrect. Correct. Yep. Because if you have t minus t1, what is t minus t1? T1 is everything in t except for 16. So when you have, it would just be 16 exactly. So that would not work. That's not going to be our T2, right? Okay. So is this helping out in terms of understanding what the terms are referring to? Okay, very good. So let's go back to the notes here. So for counting purposes, okay, so now we get to a whole bunch of symbols here. So for counting purposes, if we want to know the cardinality of the entire experiment, okay, so what experiment are we talking about? The experiment starts with t as the set of all possible outcome of trial 0. There are m trials, and the cardinality of t is also known as n. Okay, so that's how we set up all the variables or all the terms. So if we want to know the cardinality of the outcome of the entire experiment, okay, then it becomes this particular term. Well, let's find out why it is that particular term. It's a big pi notation, which means it is the product of the following. Okay, what following are we talking about? The index is I. It goes from 0 to m minus 1 because we have m trials. And since we count from 0, that's why it terminates at m minus 1 as an index value. Why n minus I? N minus I comes from here. And what is that? That's the cardinality of the number of choices for trial I. So that's why we are multiplying n minus I over the range of index from 0 to m minus 1. Are we doing okay so far? Yes? Okay. But this is not a closed form, okay? This is like some random, not sigma, but big pi notation. So what we do next is to say, well, let's try something that doesn't seem to be very smart, okay? Let's multiply what we have with big pi notation, but this time it goes from I equals to m to n minus 1, and the same thing with the other one, and then the terms are the same. Now, first of all, is this okay? Can I multiply whatever to 1 and still get the same thing back? Yes, okay. And then the second thing is, let's not look at the bottom and just look at the numerator. What seems to be related between this big pi notation and this big pi notation? What seems to be like, they seem to be related. What do you think? The indexes, right? The range of the indexes seems to be related. Well, how do you know they're related? M is on one and is also on the other one. Is that okay? But it's not just that m is shared between the two big pi notation. M minus 1 is the end of the entire range of one big pi notation, but it is the beginning. M itself is the beginning of the range of the other big pi notation, which means when you combine these two, they stack. Okay, they become one bigger big pi notation. Okay, that's a better way to do it. And that's why when you combine this pi and this pi, it becomes a bigger pi. So the bigger pi has an index going from 0 to n minus 1. Okay? And the denominator stays the same because that's artificially introduced, so it has nothing to cancel it out or to combine with it, which is fine. Okay, we'll deal with that later. So now we look at this term, okay, on the second line, and we go like, do we recognize this? Well, in this form, we do not recognize it, but we can actually, okay, let me zoom in a little bit. But we can recognize it when we shift and change the range of the indexes. Because when you look at this thing here, and you say, okay, what is the actual first value of the big pi? Well, when I equals to 0, n minus I is n. is n, okay? What about at the end? What happens when I equals to n minus 1? If I equals to n minus 1, what is n minus I? 1. Okay. So all we are really doing is multiplying n and then multiply n to n minus 1 to n minus 2 all the way down to 1. But we can write it in the other way. We can just say that we are having a product of 1 to n, which means it is just 1 times 2 times 3 all the way to n. Is that okay? But wait, we know that it's just n factorial. Is that making any sense? What about the other one? What about the denominator? The denominator at this point is starting at I equals to m. It ends when I equals to n minus 1. So we plug in the same values and see whether we can find a pattern or not. So now we ask, what is the value of n minus m? Well, there's no other way to express it. I mean, it really is just n minus m. But what about the n here? What happens when I equals to n minus 1 and we want to evaluate n minus I? I equals to n minus 1, so n minus I is 1. So in this case, we are basically multiplying m to m minus 1 to m minus 2 all the way down to 1. So when you flip the whole thing around, you can just say that, oh, we are really just multiplying all the i's, and I goes from 1 to n minus m. So we are multiplying 1 to 2 to 3 all the way to n minus m. Are we still doing okay so far? But that really is just known as n minus m factorial. So now we took the original thing, we shrink it down to n factorial divided by n minus m factorial, which otherwise is known as permutation. That's what permutation is. Well, I wrote that here. So are we okay so far with the math? So we are okay now with counting. Okay, this is really good for counting, which is basically saying, let's start with n things in a bag. Okay, and each trial is just picking one thing out of the bag, but you do not put it back into the bag for the next trial. So how many ways can we pick something from a bag? And the sequencing is important. If I pick A, B, and C in that sequence, it's different from the sequence of C, B, and A. So how many ways can we do it? Well, if n is the number of items in the bag to begin with, and m is the number of times we pick something out of the bag, then n factorial divided by n minus m, the whole thing factorial, is the number of ways you can choose things out of that bag. Are we okay so far? All right. So counting is easy. And then this part has to do with ordering. In some cases, the ordering of trials in an experiment is not important, such as in the case of a lottery. So when you're dealing with lottery, whether you pick, okay, in our example, whether we pick 16 first or 57 first, doesn't really matter. Okay, as long as those numbers are finally chosen, they're still considered the same. Okay, so how do we deal with that? Now we talked about this problem a little bit before in the previous class. So I want to express the case where choosing 1, 2, 3, 4, 5 in this particular order is really considered the same as choosing 5, 4, 3, 2, 1, which is the opposite order. Because all I really care is 1 chosen? Yes. Is 2 chosen? Yes. Is 3 chosen? Yes. Is 4, 5 chosen? Yes. I don't really care whether it's chosen first, second, third, fourth, or fifth. Is that okay? So now we are switching to the set notation, because when ordering is not important, we can represent it as a set, because how you write out the elements in a set is not important. The ordering is not important. So set is closely related to combination, where ordering is not important. Tuples, on the other hand, is closely related to permutation because ordering is important. So are we okay so far with that? Because it really helps in the future, because when you have a problem where you're given it is a set problem, then you can think, oh, it's probably a combination thing that we are thinking about. On the other hand, if it is a tuple kind of thing, then you probably want to think it may be a permutation kind of thing. Okay?
Maybe other ways? Didn't you just say that set is more like
A set is more like a combination. A tuple is more like a permutation.
So if it's in the parentheses,
Mm-hmm.
ordering matters. If it's in the little
The-
bracket squiggly things,
Mm-hmm.
ordering doesn't matter.
That is correct. Because when it's inside the braces, it is a set. And the order of how you list elements in a set is insignificant. But when you're using parentheses, then you're dealing with a tuple, then it becomes important. So are we okay so far? Okay, so let's go back to the Lotto problem. Okay, so I'm switching back to the tablet for now. And we're going back to the Lotto problem. So with the Lotto problem, without counting the power, is it called a power ball? The extra one. So without counting the power ball, n equals to 69 because there are 69 numbers that we can choose from. And the number of trials is 5 because we have to pick 5 numbers out of 69. So the first thing we know is, oh, okay, we know the permutation now. Because the permutation, okay, so we'll use this notation of choosing 5 out of 69 in terms of permutation is 69 factorial divided by 69 minus 5 factorial. That's something that we just worked out, right? Okay, but this is giving me the number of permutations, which means if I choose the numbers 1, 2, 3, 4, 5, it will be counted as one of these numbers, and then 5, 4, 3, 2, 1 will be counted as another one of these numbers. But that's not what I want, because I just want to know what are the chances that 1 is included in the selection, 2 is included in the selection, 3, 4, and 5 are included in the selection. In what order is not important. Yep. Exactly. So we know it has something to do with 5 factorial. Because given a particular set of 5 balls, okay, there are 5 factorial ways to do the permutation. So we have duplicates. So for each way of choosing 5 balls, there are 5 factorial quote-unquote duplicates or 5 factorial permutations that actually correspond to the same set within this number. Okay, so now getting back to the notes. Okay, we are reading this paragraph here. So knowing the number of permutations of an experiment, how do we get to the number of combinations? Well, it really is just trying to figure out for each combination, how many permutations can we get? Is that making any sense? So in a very concrete case, if my combination is the inclusion of 1, 2, 3, 4, and 5, the question is, how many ways can I choose these 5 numbers in different orders? 1, 2, 3, 4, 5 is one order. 1, 2, 3, 5, 4 is one order. 1, 2, 5, 4, 3 is another order, and so on. Well, that's really just 5 factorial. In this case, in a general sense, it's m factorial. So what we need to do, okay, switching back to the Lotto case, is to say, okay, so the number of combinations, this thing, is really just the permutation or the number of permutations divided by 5 factorial. Because for each combination, we have 5 factorial, which is 120 permutations. So in order to combine all of those duplicate combinations into one single, in order to combine all those 120 permutations into one single combination, we just do a division. Is that okay? So in a general equation, we just basically say divide the whole thing by m factorial. So so the number of combination is the number of permutation divided by m factorial. So when you look at the final form of combination, it becomes n factorial divided by m factorial times n minus m factorial. So you can look at this kind of as the definition of n choose m, but you can also see that how we reasoned out all of these things. It's the reasoning that is more important, because the definition, you can just, if you look at it as a definition, it's just a memorization kind of thing. But how do we get to this definition? That's the reasoning part. So are we good so far with permutation and combination? Okay. So all of this stuff, if you just look up permutation or combination, Wikipedia probably will give you all of the same kind of stuff. So what comes next is kind of unique to this class. Kind of like the function g for folding spaces. So my interest now is shifting from counting to actually enumerating. What is the difference? Counting is really just counting 1, 2, 3, 4, 5. We got a bazillion ways of organizing things. Okay, that's counting. But enumerating means if I give you 6 balls, okay, 1, 2, 3, 4, 5, 6, and I ask you to choose 3 without replacement, okay, give me all the possibilities. List all the possibilities. Don't just count how many. I want the actual possibilities. How would you come up with that? Okay, so let's make the problem smaller, and we'll figure out what kind of problem we are trying to solve here. So I will go ahead and start with the original t is, I have to make this smaller because otherwise it may not be easily doable in the class. So we'll just say 1, 2, 3, 4. There are 4 elements in t. So n equals to 4. And I will say m equals to 2. In other words, we only have 2 trials. So given the original set, or the set of possible outcome of trial 0 is 1, 2, 3, 4 as a set, and I have 2 trials to perform in this experiment, give me all the possible outcomes. So how would you do that? You can do it in many ways. The first way is graphical, because I think a lot of people are visual, so the graphical way is the easiest way to go. So the graphical way is really just like that. I can pick 1 as my first outcome. I can pick 2 as my first outcome, 3 as my first outcome, 4 as my first outcome. Okay? After the first trial, let's move on to the second trial. After 1 is selected, I only got 3 choices left for my second trial. So in this case, my second trial is 2, 3, or 4. In this case, 2 is chosen. So in my second trial, I can only have 1, 3, or 4 as the possible outcomes. Okay? So you can probably see that this is not really that exciting of an exercise. So if the question is asking, give me the set of all possible outcomes when t is 1, 2, 3, 4, and the number of trials is 2, what is that going to look like? Well, the set of all the outcome of the entire experiment is really just going to be the 2 tuples representing 1, 2, 1, 3, 1, 4, 2, 1, 2, 3, 2, 4. You can see how this is somewhat boring. 3, 2, 3, 4, 4, 1, 4, 2, 4, 3, and that's the end of that set. So my question is, if I say t is 1 to 69 and m is 5, how do you generate this set? I surely hope no one is going to try to do it by hand. Because that's going to be, it will take a while. So, yep. You can do it recursively. Okay. So, but in terms of, remember this class is kind of like a math class. So I have to do things in a mathematical way, right? In other words, instead of explaining the concepts to programming students, I have to be prepared to explain the same concept to mathematicians. So how do I explain the recursive way of generating all the possible outcomes of an experiment like this to a mathematician who may not know about programming at all? So how do we do that? Summation. Yeah, we use notations like that. Very good. Exactly. So this is how I would do it. So I first introduce the term of big omega. And by the way, omega in the context of discrete probability has a different meaning compared to omega in propositional logic. Omega in propositional logic is the set of all the operators. In discrete probability, omega is the set of outcomes. Okay, so in the context where we are now, omega is the set of outcomes, not the set of operators. So what I do is I put a subscript to omega, and so omega I as a subscript t is representing the outcome set of an experiment involving I trials. Okay, that's all it means. And t is the initial set for trial 0. That's our starting point. Is that okay? In other words, at this point, I just want to make sure everybody understand what is omega I in parentheses t. Is that okay? It's the set of all possible outcomes when we have I trials, and the first trial has t as the initial set. Is that okay? So in the case of lotto, okay, in the case of Super Bowl or Powerball lotto, then t is going to be a set of numbers from 1 to 69, and I is going to be 5 because we got 5 trials. We have to pick 5 balls. Okay. So with that notation, then we can go, So let's try to find out what is omega 1 first. Omega 1 is basically saying we only got one trial. This experiment has only got one trial. And t is the initial set for trial 0, or the first trial. So tell me what is the possible outcome of all of this experiment. Well, it's just t itself. Is that making any sense? Okay. So omega 1 t is just kind of by default. Question?
So does the index not start with 0, it starts with 1?
It starts with 1 because we are counting the number of trials. So it's not the index of the trial, it is the number of trials. Okay, so if omega 1 t is just t itself, what about omega 2? So this is how I express omega 2. So omega 2 of t is the big union, okay? So in other words, we are having a union of a lot of different sets. What are we unioning? In other words, what are the sets that are being unioned together? So we have E being an element of t. So for each element E of t, we want to compute this term. What is this term? It's E by itself, and then Cartesian product with t minus, in parentheses, E. What does that mean? Okay, how is this going to work out? Well, what about this? We'll use this notation on the problem that we just solved using the representation of a tree. Okay, so now we can say, oh, okay, it looks like this tree in one particular way of looking at it. But what about if we look at it from this kind of more mathematical definition, what is it going to look like? So I'm going to switch to the tablet for now. So I switch to the tablet. We are still dealing with the same problem, but this time we're doing it symbolically instead of using a tree and graphically. All right. So in this case, t is still the same: 1, 2, 3, and 4. Right? Okay. So the first question is somewhat trivial. Omega 1 of t is what? What does that mean? Okay, we are looking at the outcome of an experiment that only has one single trial. And for the first trial, the initial available elements is t itself. Well, we know it is just t itself. So it's just 1, 2, 3, 4 as a set. 1, 2, 3, 4 as a set. No problem, okay? It makes sense. So now we want to look at omega 2 of t. So omega 2 of t is kind of like, we can choose 1 as the outcome of the first experiment. If we do choose 1 as the outcome of the first experiment, what can we now choose as the outcome of the second trial? 2, 3, and 4. Okay, very good. Okay, so we can say multiply Cartesian product with the following. So I could easily just write down, the set of 2, 3, 4, but I don't want to do it that way because I want whatever is here to relate back to whatever I have chosen to begin with. So what am I going to do? I'm just going to say whatever omega 1 has minus whatever I have chosen. Is that making any sense? Now, but this is only going to give me the possible outcomes that starts with 1. If I chose 1 from my first trial, this will give me all the possible outcomes of the experiment. But I don't have to choose 1 as the first outcome. I can choose 2, okay? So the second line is just going to say, but what if I choose 2 as the outcome of the first trial? Then what do I have available for the second trial? Oh, okay, that's not too hard to understand, right? What if I choose 3? Fine, same kind of deal. And what if I choose 4? Right? Okay, so the first line will give me a set of the tuples 1, 2, 1, 3, and 1, 4. Does it make sense? Because omega 1 in parentheses t is really just t itself, which is 1, 2, 3, 4, minus the set of 1 will give me 2, 3, 4. So the Cartesian product between the set of 1 and the set of 2, 3, 4 would just be the tuples 1, 2, 1, 3, and 1, 4. Is that part okay? The second line is going to give me what? The set of the 2 tuples 2, 1, 2, 3, 2, 4. The third line is going to give me the set of 2 tuples 3, 1, 3, 2, 3, 4. And then the last line is going to give me the 2 tuples 4, 1, 4, 2, 4, 3. Is that okay? But somehow I have to combine these sets because they're all a part of omega 2. Is that making any sense? So how do I combine those things? Union. Okay, so we just union all of these things together. 1, 2, 3. Is this looking a little bit familiar? Okay, so the more concise way to express this is now to say, oh, we have a big union, okay? What are we combining, with this big union? What does each term look like? Each term is going to look like, well, we'll just say that some kind of element in curly braces, Cartesian product with omega 1 t, okay, because that part is common to all the lines, minus the set of just E by itself, okay? Is that okay? Because this is just an abstraction of what seems to be common between these four lines. Is that okay? So the next question is, what E are we talking about? Well, these E's, 1, 2, 3, and 4, turns out to be what is available in omega 1t. Is that okay? So now I just have to say, in terms of quote unquote the index, E for each E in omega 1 of t, do the following, and then make a big huge union out of it. So are we doing okay so far, going from the concrete case back to the equation or the expression that I used earlier? Yep.
So if it would be omega 3t,
Uh-huh.
would it be the same thing, but we're just doing that?
Oh, I like that question. Okay, so let me repeat that question first so it's recorded. So the question was, what about omega 3 of t, right? So what do you think omega 3 of t is going to look like? Okay, so I hope everybody has this written down because I'm going to do something here. Is that okay? Okay. So, well, okay, I'll be kind and not erase anything. So I'm going to use green to say, what if we're dealing with omega 3? Okay? So instead of omega 2, we now have omega 3 here. Is that okay? So what do you think is going to be, omega 3 is going to look like? Yep. So this is going to be omega 2. Omega 2. It's a recursive definition. Is that okay or not? But does it make sense? Does it make sense at all? I mean, so let me give you the more general equation, and then you guys can say, does it make sense or not? So in general, once we have a generalization, we say omega k, okay, of t is the big union of E as an element of omega k minus 1 t. And then we have exactly the same thing inside, which is E as a set, Cartesian product with omega k minus 1 t minus minus E as a set. 1, 2, there we go. Okay. So we look at this and go like, does it make any sense? I think I'm missing a close paren here. So we'll just add that. There we go. Okay, does it make sense? Omega k is saying, give me all the possible outcomes of an experiment that has k trials. Okay? And t is what is available to the first trial. Okay, that's what omega k t means. Okay? So then you look at the rest of the equation. We're unioning a whole bunch of stuff. What are we unioning? Well, we are unioning whatever omega k for each element. Ooh, okay, I made a mistake here. Okay, I made a mistake. So erase that, and probably that too. That really is t. And this is also t. Okay, there we go. Okay, so let's see if this makes sense or not. We are looking at the outcome of an experiment where we choose things without replacement. There are k trials. The initial set available of things that are available is t. Okay, so that's what we're interested in. The union, the huge union, is basically saying, let's pick each element out of t and make a subset out of it. Okay? What subset are we talking about? Okay, we pick E from t, And then we say, okay, now that E is chosen, I cannot use E anymore in the subsequent trials. Oh, okay. The other thing that I forgot about here, um, eraser, that we go. So that makes more sense. There we go. Okay, so we have to make the same change over here. There we go. Now it makes more sense. All right, so um, so this is what I have chosen for the first trial. What do I have left available for the rest of the trials? T minus E, right? Those would be the elements left available for the rest of the trials. But I have to combine this E with all the tuples of the subsequent trials. But how do I express the outcome of the subsequent trials? Well, we just look at that and go like, oh, we'll call that a sub-experiment. What sub-experiment are we talking about? It's a sub-experiment where initially it has T minus E elements available, but it only has K minus 1 trials. Is that making any sense?
So if you only have one trial, you won't have the three.
If you only have one trial, you wouldn't have.
I forgot what the little funny shape is. It's called. It has funny shape, 2 parentheses, T parentheses, omega.
Omega.
You don't have omega 3 if it's only one trial.
Yep.
You just have the.
So by definition, when you only have one trial, then omega 1t is just t itself. You get t back. And just to be correct here, I forgot about this part, so I have to fix all of these and close the paren. Oops. Correctly. There we go. In this case, it turns out to be the same, but this is the correct format. You have to do the subtraction before you apply the omega to it. Yep.
We need to go like recursively, right?
Yep.
Omega 1, omega 2. We cannot jump to from omega 3 to omega 6.
From omega 3 to omega 6. So omega 6 depends on omega 5, omega 5 depends on omega 4, omega 4 depends on omega 3.
Right. So it just
It's just recursive. Yep, exactly. Yep.
So omega of n, say like omega 5,
Uh-huh.
we pass in our original set of numbers t.
Mm-hmm.
Omega 5 would then have available any element from the original set. Omega 4 would have a smaller set, omega 3 a
Yep.
smaller set. But doesn't that mean our fifth trial would have more possible outcomes than our first trial?
Well, let's find out. Okay, so we'll go ahead and use the lotto example. So we'll keep this definition around, and then we'll say omega 5, the set of 1 to 69, because that's the problem of the lotto game. Okay, so by definition, this is now the set of 1 Cartesian product with omega 4, but now that 1 is chosen, I have basically 1 to 69, oops, 1 to 69 minus 1. Is that making any sense? If I chose 1 in my first trial, then I have a sub-experiment of 4 trials left. And then but the choices available to that sub-experiment would be everything that was available to me minus what I have chosen for the first trial. Go ahead.
So omega of n, the n doesn't mean that's our trial number.
And the n, this means the number of trials.
Not the number, the specific trial we're working on.
Correct. It means the number of trials that we need to figure out, not which trial we are dealing with. Yep. Okay. But just to finish this, right? So the next line is going to say, but what if we choose 2 as our first, as the outcome of the first trial? Then we have a sub-experiment with 4 trials left. But what numbers are available this time? Well, it's 1 to 69 except for 2 because I just chose it. Does that make any sense? So I can do dot 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 all the way up to, what if I choose 69 in my first trial? Well, then I have a sub-experiment of 4 trials left. But what numbers are available in the sub-experiment? It'll be 1 to 69 minus 69 itself, because that's what I have chosen for the first trial. Each line is representing a pretty big set of 2 tuples. So the first line is going to be 1, 2, 1, 3, 1, 4, all the way up to 1, 69. The second line is going to be 2, 1, no 2, 2, 2, 3, all the way up to 2, 69. The last line is going to be 69, 1, 69, 2, 69, 3, all the way up to 69, 68. So each line is representing, yep. Oh, I take it back. It's not just 69. It's the entire. It's a whole bunch of stuff that we are cross-producting this with. So we take. Okay, go ahead. Let me answer that question first.
I was just gonna
Hmm?
I was gonna go back to the so as it recursively
Yep.
goes on. So like for example, omega 3, when you do like the element, each element of t Cartesian product, like the previous
Yep.
omega of t1, that's gonna give you a bunch of 2 tuples. So would that mean that your next 2 tuples are gonna
Yep.
have 2 tuple as like
Correct.
like one column
Now,
2 tuple,
exactly.
another 2 tuple.
Do you remember?
Yeah.
Do you remember when we first introduced the concept of 2 tuples or Cartesian product? I already raised a question of, do we have nested 2 tuples or do we merge 2 tuples into a longer tuple?
That's what I was wondering.
So we merge in this case. We just merge.
Okay.
Okay. So okay, but I made a mistake in my description here. So now, on the first row, now we have to look at this and say, what is that? What does that look like? Okay. So now we look at that. We have an experiment of only 4 trials left, and what is available to me is technically there's just 2 up to 69. But what is it going to look like? What do you think? We apply pretty much the same thing. We say, what if we choose 2 to begin with? What if we choose 3 to begin with? And all the way up to, what if we choose 69 to begin with? And then we have to do the Cartesian product. Cartesian product with what? The sub-experiment of only 3 trials left, right? But what is available for the omega 3? It's everything that was available to me minus what I have chosen for the first trial. Same thing over here. Omega 3, everything that was available to me minus what I have chosen for the first trial. And then the same thing here. So this would be 2 to 69 minus 69 as a set. So we union all of these things. Oops. And then we have to union all of these things too. So then we have another problem to solve. What is omega 3 of 2 to 69? What do you think that's going to look like? About the same thing, right? Except the available choices is now shrinking by 1. So every time we go from omega k to omega k minus 1, there's 1 fewer element available to the sub-experiment, because I'm taking 1 for the trial, for the first trial of this particular sub-experiment. Is that okay? Yep.
Basically, the answer for omega 5 is going to be unions of all of this big, of like union
It-
of omega 5 union omega
Oh, it's going to be pretty ugly because omega 4 of 1 to 69 minus 1 expands to this, right? Omega 3 expands to some ugly, big, huge union. Yes. Yep. So you have to Cartesian product everything back to omega 5 in this case. Yep. Is that okay? But is the concept okay? Because it's the idea or the concept that is important. Okay, how many people feel comfortable with recursive definitions or recursive algorithms? Okay, this is basically one way of looking at a problem. Okay, one way to look at this is to say, okay, so let's say somebody asks me, okay, and say, Tech, I want you to give me all the possible ways of choosing 5 numbers out of 69. I look at that I look at that problem and go like, man, that's a really big chore. I don't want to do this. Tell you what, I will handle the first trial. In other words, I'll say, okay, what happens if I pick 1 first as my outcome as the first trial? What if I pick 2? What if I pick 3? And all the way up to, what do I pick? 69. Okay. So let's say I pick 1 out of the 69 numbers to be the outcome of my first trial. And I go like, man, I got 68 things left and 4 trials left. I don't want to do that. Why don't you do it? Okay? So what is the problem that I'm passing on to you? Well, what numbers are available to you? 2 all the way down to 69 are now available to you. But what is the number of trials that you have to deal with? Not 5, because I dealt with the first trial. So you only got 4 trials left, right? So to you, the problem is now omega 4, but the set is 1 to 69 minus whatever I have chosen in my trial. So what are you going to do? You look at the problem and do exactly the same thing that I did. You go like, I can do the first trial with this experiment, but somebody else is going to do the rest of the experiment, right? That's the whole idea of recursion. You're breaking down a big problem into sub-problems. Now, that's no big surprise, but in this case, each sub-problem has the same nature as the original problem, and that's why you can reuse the same approach to break it down further and further and further until you get to the base case, omega 1. So let's say we get down to the base case, which is going to be 5, 4, 3, 2, 1. Okay, that's you. So you get to handle the base case. So what does the base case look like? It's omega 1, which means you have to run experiments. How many trials? 1 trial for your experiment. What are your choices? Let's just say it is that I have chosen 1, 2, 3, 4, 5. 1, 2, 3, 4. So yours is 5 to 69. Okay? So what is your answer? If I ask you, give me all the possible outcomes of an experiment that only has 1 single trial, and the initial set that you can choose from is 5 to 69. So what are you going to give back to me as an answer? 5 to 69. Okay? So you're going to give that answer back to the previous guy who is responsible for an experiment with 2 trials. Okay? So once you figure out everything that you need to figure out, you pass that answer back to the guy who's responsible for an experiment of 3 trials, 4 trials, and then back to me who's responsible for an experiment of 5 trials. So that is that's the magical part of recursive algorithms, because you're breaking up a big problem into sub-problems that have exactly the same nature. Yep.
Professor, but like in the end of all this, we'll have to multiply. We'll have to do Cartesian product between a set of numbers, like just of a number, 1 number basically, and the set of a bunch of tuples.
Yeah. Yep. Yep. And that's why he asked that problem, that question of when you have a Cartesian product of a set of just a particular item and a set of tuples already. So do we have nested tuples, or do we just merge the tuples so that it becomes a longer tuple? In this case, it just becomes a longer tuple. All right. So So the answer that I'm going to give to any mathematician is just going to be, where is that? Here. So the answer has two parts. The first part is when the recursion stops, which is this part here. If you just ask me to run an experiment with one single trial, I can tell you right away, okay, the outcome of this experiment is just whatever t is. That's the end of recursion. What if the number of trials is more than one? Then I would use this approach. So this is the general approach of what we just talked about. Okay? I'm responsible for an experiment of I trials. Okay? And the first trial that I'm responsible for has t as the available t is the set of the available possibilities or outcomes. So what am I going to do? I'm just going to say, what if I choose this element out of t? Then it will be this kind of elements left, t minus e, available to the next or the sub experiment. Find out what that sub experiment is going to return to me, cross product or Cartesian product with e. Then I get one row of two tuples. What if I pick another element out of t? Another bunch of elements, another bunch of two tuples, and so on. So that's how this approach works. So here's my question. Do you think a mathematician can understand this? Probably so. Because there are a lot of mathematical problems that are actually recursive. So are we okay so far with this? So once we are done with the resolution homework assignment, this is going to be your next homework assignment, is to write a program to generate permutations. That's not what? It's not as complicated as you think it is. So are we okay so far with this? Okay, so the next question, we do have 4 minutes left. Why do I want to know the outcomes? Why do I want to generate all the possible outcomes? I mean, with what type of program do I need a mechanism like this? Has anyone played Mastermind, the board game? Okay. So what do you think about writing a program to play Mastermind? Now, if you want your program to come up with the secret combination and score your guess, it's actually really easy. Do you see what I mean? Okay. Let me just go to the Mastermind game so that I can show you what I mean by that. So Mastermind board game. And there are online versions of this game too. You can actually play online. So let me just go ahead and play online. This may be a playable one. Yep. Colorblind friendly. I don't need that. Okay, so we start a new game, and then we can basically pick out the colors. So in this particular case, the computer has chosen a secret code, and my job is to guess what the secret code is. So it's a code breaker kind of game. So I can just pick some random colors. So the first guess is usually just kind of somewhat random. So in this case, I'm just going to pick blue, green, orange, purple, and I ask the computer to check it. So the computer comes back with a score with 1 black peg and 1 white peg. What does that mean? The black peg means one of these 4 is the right color at the right position. Okay? The white peg means another peg, okay, has the right color but at the wrong position. But which one is which one? It doesn't say anything. Okay, so it can be any one of these 4 that is at the right position, and the right color, and then it can be any one of the three that is of the right color but the wrong position. I have no idea which one is which one. Okay? But I know two of them is quote unquote right. Okay? So what do I do next? I would go like, well, let's assume the blue is right, okay, at the right position and the right color. And let's say purple and orange are the wrong ones. They're not the right colors at all. So I'm going to guess a yellow, and I'll shuffle the positions of the other ones. So which one do you think is the right color at the wrong position? Green, okay, so we'll move the green over here. And then we also need one more color, which is red. Okay? In other words, what I need to do is to make sure that this particular guess here is consistent with the score of the previous line. Okay? And this one is, because if the actual hidden code is blue, yellow, green, and red, I would have gotten that score on the first line. Is that okay? So now I say, okay, computer, cross-check. Did I get this right this time? Ooh, it's even worse. But it's still giving me more information. Now, because of these serving as constraints, what I can possibly use on the third row is now even more severely limited, and so on. Is that making any sense? So how do I play this game in reverse? In other words, I'm the one who is holding a hidden pattern, and the computer is the one who's trying to guess. So how would you write a program to guess the pattern when I'm the one hiding it, but I'm giving you hints? How would you write a program like that? It's called, yes?
Like form a tree of all possibilities, you can start chopping off subtrees as you know that they cannot be possible.
Exactly. Or if you do not want to store the entire tree, which can take up a little bit of memory, you basically just regenerate all the possible combinations, or excuse me, all the possible ways of arranging the colors, and then you subject each one to the previous tests and see if you get a consistent score. If you don't get a consistent score, it cannot possibly be the actual answer. You chuck that one. So as soon as you find one that is consistent with all the previous guesses, then you can use it. Now, it's not optimal if you do it that way. You might end up actually using more guesses than you really need to, but that's one way to do it. This approach is called generate and test. Okay, generate and test means you're generating all the possible things, and then you're testing and you rule out the ones that cannot be the answer. So when you're trying to deploy a generate and test approach, then it suddenly becomes important to be able to generate all the possible outcomes, because then you can apply the generate and test strategy to get something done. Is that okay? All right. Okay, so we are running out of time today, so I'm going to leave this in your mind for now. We have a long length of time between this class and the Monday class. So please read ahead of me and make sure you understand all the terms. And if you have any questions about the definition of the omega thing, think about it over these 5 days. And if you have any questions about that, ask those questions on Monday. Okay?